All right, so today's presentation is on use of shredded tires um, as a drainage material in landfill covers. I'm going to present this webinar, but this work is based on master's thesis done by Arvind Marella. And I want him to introduce himself and say a few words about himself. Arvind?
Greetings, everyone. Thank you, Dr. Reddy, for introducing me. My name is Arvind Marella. I've been a student of Dr. Reddy since 2000. I completed my master's thesis under his guidance in this very topic that Dr. Reddy is going to share today with the forum. I'm really happy that I was able to complete my master's thesis. Dr. Reddy is an incredible professor with high knowledge and wisdom. He has great studies and vision. I'm so grateful. He took me under his wings at UIC and guided me through this master's program. And because of his guidance and kindness, I believe my career is heading in the right direction. I'll always be thankful to you, Dr. Reddy. As of now, I'm actually, I have a startup company, and his guidance and mentorship actually is evident in the business I started a few years ago. Company name is called Star Geoenvironmental. Because Geoenvironmental has been the backbone of my career. The master's thesis was a wonderful opportunity for me to grow my career in this area. And thanks to Dr. Reddy for introducing me this terminology, geoenvironmental. Yeah. Without much further ado, Dr. Reddy, over to you.
Okay, thank you so much, Arvind. So thanks of you for coming today. So this is the work he has done for his master's thesis some years ago. I don't want to say which year it is, but it was several years ago that he did it. And I'm happy to share that work. And hopefully this will give you ideas on doing research yourself if you are interested in, and if you can identify this as a problem to address. All right, so my presentation title is use of shredded scrap tires as drainage material in landfill cover systems. We did some lab investigations and then we applied in the field, so you can see how lab research could translate into field application and then solving the real world problem. So I chose this one to demonstrate that research could translate into field application and solve the real world problems. So as I mentioned, Arvind Marella was the master's student, and he did all this work, and he was assisted by other graduate students that I listed here. And this is the collaboration with Tim Stark from our sister campus. And then funding is obtained from Illinois Department of Commerce and Community Affairs and Illinois Environmental Protection Agency. So in my presentation, what I'm going to do is give you a brief intro to the problem of scrap tires. And then I'm going to give you the intro to problem of abandoned landfills. And our project goal was to resolve these two problems. And how are we going to do that one? By using the shredded tires as a drainage material in these landfill cover systems. And I'm going to explain lab investigations where we, studied the properties of shredded scrap tires, and we looked at clogging potential, we looked at transmissibility, and we did some interface shear strength, hydrologic and compressibility analysis, and then we applied our proposed system in the field, and we monitored it. And so I'm going to share all that, and then finally a closing comment. So problem of scrap tires you may know, or it may or may not be a problem in the place that you are in, but you should look into this. But in the US, it's a big problem. We generate about 290 million scrap tires every year. And we already have 2 to 4 billion tires stockpiled all over the US. So we have already a lot of stockpiles of these scrap tires, and on the top of it, every year we are generating a lot of these, new scrap tires. And if you look at overall municipal solid waste, scrap tires may not be the major components, but still, these scrap tires must be managed properly because there are a lot of adverse issues otherwise. So what do we do with the scrap tires? So obviously we have been, taking to landfills and disposing them off in landfills. And by doing so, what we are using up a lot of landfill space, which is not good. As landfill space is premium these days because the number of landfills are reducing it. And also, you will have uneven settlement wherever you have tires. You may have more settlement, and where you don't have tires, you have less settlement because you're randomly, disposing these tires in the landfill. The other biggest problem with disposing tires in a landfill is that you have tires, right, and you have a lot of that open space where gases get trapped, and with the gas pressures, these tires will try to float towards the surface. They move towards the surface, and there are cases where they popped up from the covers. So they are not stable because the gas trapping, and because you have a void space within the tires, and then that's where all the gases get trapped, and then all the gas pressure pushes to these tires, coming to the surface. So it's a huge problem that it was found. So as a result of these issues, many states, state governments have required shredding of tires before disposing in landfills. You have to shred the tires so that you don't have this problem of gases trapping and then floating and then breaking off the final cover. So you cannot now, you cannot dispose of a scrap tire as it is in a landfill. So you have to shred it. And some states even require shredding and disposing in a monofills. There are special landfills where only shredded tires are disposed of. There are very few of them, but most of the shredded tires, generally goes to regular municipal solid waste landfill. And because you have to shred, before disposing, people didn't want to do it. And as a result, there were illegal stockpiles and dumps all over. Before, they were taking it to the landfill and disposing them. But now, you have to shred them, and shredding is going to cost money and effort. So people are just, accumulating and creating stockpiles all over. And having stockpiles of these, scrap tires is not a good thing. So, if you have a stockpile of tires, you could have moisture trapped in those tires, and those would be the, the breeding ground for mosquitoes and other animals and other things. So it's a huge problem. And addressing these health issues arising from this, it costs millions of dollars every year. And there are fire hazards. They could self-ignite, and then you could have these tires could catch fire. And if a stockpile catches a fire, you will see a huge smoke cloud in the air, and all kinds of toxic emissions comes out of that. This is the situation, in nearby Chicago, and putting off the scrap tire fire is a really challenging thing. So these are, again, it costs a lot of money to address these fire hazards. And there are a lot of associated health hazards, pollution, and also, aesthetic nuisance with this scrap tire. So first of all, it is not legal to stockpile. And if illegally you stockpile, then these are all the issues that are costing a lot of money on an annual basis. So we should, avoid having these stockpiles. So what do we do? If we don't want to dispose in a landfill, we don't want to stockpile, what can we do? So there are nice markets for scrap tires reuse. So one of them is the tire-derived fuel. Basically, you chop these tires and then burn them and create energy out of them, right? And then there are applications where you just, create a ground rubber and use it in applications. A lot of, playgrounds have this kind of ground rubber. And civil engineering applications can utilize this material, these scrap tires, quite nicely and in large quantities. One of the problems that civil engineering applications didn't take off before was that, they didn't want to shred the tires. The best way to use in civil engineering application is to shred the tires and use it as a tire-derived aggregate. So it's called TDA, right? But they didn't want to do that because you have to shred it. So rather than shredding, they were disposing old tires in landfills. Now they have to shred it. So if you are going to shred it anyway, why not, instead of disposing in a landfill, why not use it as a beneficial civil engineering material? So because of that requirement to shred has attracted more civil engineering applications these days. But there are other minor markets for these scrap tires, but that's not much. But this TDF, ground rubber applications, also, very limited use. But TDF application and civil engineering applications are becoming the dominant markets for scrap tires use. So this is, may not be exactly reflecting the current situation, but this used to be the situation when I had the statistics. So about 52% is used as RDF, TDF, derived fuel, and then about 30% was being landfilled or stockpiled or illegally dumped, and some part exported, and some cum rubber applications and civil engineering applications were 4.7%, and then miscellaneous applications 1.4%. So now, it's shifting. So basically, you don't want to have this landfills, landfilling or stockpiling or illegal dumping. So we want to use this one as much as either fuel or more potential to use as a civil engineering applications. In the state that I am in, Illinois, in the US, currently we don't have any civil engineering applications. So we basically have a lot of this tire-derived fuel. So we just chop them and then burn them for energy. Even as you see, this TDF is a huge market, but there are many problems associated with using TDF that makes civil engineering applications much more interesting and attractive. The reason why, it's not easy to use, this scrap tires as tire-derived fuel is you need to chop them into small pieces. And shredding, tires into small pieces is going to cost a lot of money because you have to shred it again and again and again to make sure that the tire chips are a small size that is needed for TDF. And if you compare the cost of this using shredded tires versus other competing fuels, this cost comes out to be almost the same. So why would people use shredded tires when they can use other standard fuels? If there is a huge cost advantage, then they will use the shredded tires. If there is no cost advantage, would somebody use it, right? And also, these because you're burning tires, you need a major environmental permit in those facilities where these are being used as fuel. And also, these facilities have to monitor emissions, right? Because they could have a lot of toxic emissions coming out of burning of the tires. So you need to monitor and make sure you comply with the permit requirements. So that's going to be additional costs that you're going to incur. And reliability of supply in remote locations. If you have this plant somewhere to burn these tires for energy, how do you get all these scrap tires? And if the location is in a remote area, how do you get all the tires in the quantity that you need to have a continuous operation of these facilities? And the costs associated with transportation. So these scrap tires are generated all over, and you need to have them collected and transport to the facility that you're going to burn. And that's also is a big problem. So these are all the concerns that a lot of state agencies, all the parties that are involved in management of scrap tires are looking at it. So that's why this also other thing that I want to mention is nobody wants to have these tire burning facilities in their local community, because they know that these emissions could be very toxic. So as a result of these issues, everyone, all the agencies responsible for scrap tire management are looking into civil engineering applications. And civil engineering applications are good because here we can consume large quantities of the scrap tires. So we can use scrap tires as an embankment fill material, road-based fill material, retaining wall backfill material, vibrations isolator, thermal isolator. We can use in septic tanks, chemical absorbent, landfill gas collection trenches, landfill leachate recirculation trenches. So there are many applications, but I'm just listing few of them here that it is possible to use, right? So, and you could think about many creative applications for these materials. So you are using this material as a useful material, and also you're solving the problem of scrap tires. And a lot of interesting projects are going on in terms of civil engineering applications. So people are using as an embankment material because it's a lightweight material, high shear strength, very good drainage. So people are using it, especially if you have a soft soil conditions, foundation conditions. You're reducing the weight of reducing the loads. So people are using for the slope retrofits. So if you have a slope, and here, in this case, the slope failed and they excavated out the soil, and then they put in these shredded tires and then creating the stabilized slope. Because the less weight of these shredded tires will make it stable. So in landfills, for leachate gas collection systems, leachate recirculation systems, you need trenches. You generally need a drainage media there. So instead of using sand or gravel, they're using shredded tires. And the retaining wall backfill application is one of the major uses of shredded tires, because if you use behind the wall, you have less unit weight and then high friction angle. So you will have less earth pressure on the wall. So you have economic design, and it's a free draining material. If you put a weep holes, then you're not going to have any drainage issues. And also, you can ensure active pressure conditions, because these tires are compressible, so they can yield and get you the active conditions. So it's a very nice application, and people are using for that. And here is another example of use of retaining as a retaining wall backfill. And they use shredded tires as a for vibration isolation, thermal insulation, and so there are many applications that are coming up for civil engineering. So one thing I want to mention here is mixing shredded tires, tire chips with soils, like even sands, and more importantly, clays, is impractical. I see a lot of research that is being done, or I see a lot of papers that are published. You could do that one in the lab, right? I mean, you can have very finely chopped tires, and you mix it with the sand or clay. In the lab, it's easy to mix it and then do the testing and all those things. But you think about in the real world, how are you going to do it? How are you going to mix it uniformly? Let's say I say, I'm going to use this mixed proportion. I want to have 50% soil, sand, 50% shredded tires. How are you going to ensure 50-50 in the field? How do you mix it? Especially how do you mix it with a clay? So I see a lot of research with scrap tires mixed with tried chips mixed with soils. Those are all research studies, good for publications, but I'm not saying that it's impossible to use it, but it's practically difficult. If you look at it from a construction point of view. And also, you don't want to use very fine chips, small size chips. Again, for lab experiments, you need only small quantities. You can get, tires chopped up as much size as you want. But in real world, if you have to have that small size, it's going to cost a lot of money in terms of setting operations. So that's about, the problem of scrap tires and how civil engineering applications are becoming more common. Now, in addition to scrap tires, we have a second problem in the state that I am in. It's a problem of abandoned landfills. So the state has done a survey and found that there are 33 abandoned landfills in Illinois that need some attention, because there are a lot of problems with these abandoned landfills. There's exposed refuse, odors, gas buildup, slope instability, surface erosion, leachate seeps, groundwater and surface water contamination. So, state has identified that these landfills need some remediation. So how did these landfills arise? Because when the new regulations came in, strict regulations came in, these had to be either closed, these had to be closed, or they're retrofitted to meet the new regulations. So a lot of these landfills, they didn't want to retrofit, and so they just abandoned them. And they didn't even put a proper cover on the top of it, and then they left it. So the state has become responsible for fixing these things. And state did some analysis on these landfills, and this graph shows the problems at these landfills. I hope you can see the bottom, but what I'm showing is inadequate cap, exposed refuse, leachate, groundwater contamination, surface water contamination, erosion, fires, vectors, odors. And we have problems now, but if you ignore these problems, the problems are going to become worse and worse. So that's what this graph shows. So the problems, even the new problems, are going to arise if these are not going to be fixed. So it's important to fix these abandoned landfills. So I'm going to show you some pictures of of the issues at these landfills. So here is open dumping and poor side slope conditions. And here you see the exposed refuse. And here you see exposed trash. And here you see abandoned drums at the landfill. And here is again at another landfill, how the refuse was exposed. And here is, you can see, the cap, they didn't put it properly, and a lot of erosion. And then you can see, in some places it's deep gullies exposing the waste. Here is the, poor contouring, no proper drainage, no proper vegetation on the top of the landfill. Um, Here again, poor cap material, and there's no vegetation growing on this. Again, poor cap material with exposed refuse and no vegetation. Here is a poor capping. Uh, Grading is not proper, and so all the surface water is ponded. A lot of leachate seeps at some of the landfills. Uh, there is another leachate seepage situation. Here is erosion gullies and making the leachate problem worse. Again, it's a leachate issue here that I'm not sure. I'm showing these landfills, these situations at different landfills. So there are 33 of them. So each of them have these problems, one or multiple problems. Um, and some of these landfills, they are very close to houses. So for example, in this case, the refuse is very close to the home. So you see on the top here, there are houses within 50 feet of this abandoned landfill. So here is the erosion with the leachate problems. Here's the erosion problem, the leachate seepage problem, and a lot of erosion. And you don't see it here, but on the right side is the abandoned landfill, and see the sign that is put in. So the analysis showed that this slope gets fail at any time. So it's a problem. So it's a warning for people going on the street. So hey, be careful with this unstable slope. So these are the biggest problems that they found at these 33 landfills. And what state government did is they came up with a new program, legislative program called Illinois First, and they allocated $50 million to fix these 33 landfills. So, and then the state government has taken the responsibility to clean up these landfills. So there's always, money makes the difference, right? So if you have money, you can resolve all the problems. And of course, you need to have people who can, have that vision of understanding the problems and hoping to solve those problems. So we thought about these two problems, scrap tires and abandoned landfill problems that we have in our state. And we wanted to solve these two problems with one solution. So the solution that we came up with is a capping system, a simple capping system, which has the three layers. You have a barrier layer, and then you have a drainage layer, and then you have a cover layer. So we are proposing these to be used on all the abandoned landfills where, of course, this cap is missing, or the cap that you have is inadequate. So the barrier layer is to minimize the infiltration of the water, whenever it rains, so it does not go into the waste and it does not create the leachate. And it also does not allow the gas to escape. And there's a gas collection system, the gas wells, and that also goes with this cover system. And the drainage layer, so for the barrier layer, you use the on-site clay soil. For the drainage layer, you need to put a drainage layer because that will allow any water that is infiltrating from the top layer to be drained out to the sideways and discharge it, because it's not touching the water, it's touching the waste, so it's clean water, and you can put it in any surface water bodies. So you don't need any treatment for that. And also, because you are taking out the water all the way, if you didn't take out the water, then there could have been accumulation of the water on the barrier layer, and then you could have excess pore pressures and seepage forces, and that would have endangered the stability of these slopes. So it's going to work as a drainage function as well as enhance the stability of the slopes. which is much needed. So typically we use sand or gravel for this, but instead of that, can we use shredded scrap tires because we have a lot of scrap tires to get rid of. And then the top layer is a vegetative layer or cover layer, we call it. Basically, that will allow the vegetation growth. It will promote the evapotranspiration and also prevents the erosion. As you saw that one in all those slides, all those pictures, the erosion has been a major problem. So this will resolve that problem. And then we can, use the on-site clay for that one. So only material that we need to transport to the site, is this shredded scrap tires. So that was the concept that we wanted to pursue. The research question here is, can shredded scrap tires be used as effective and economic drainage material in the proposed landfill cover system? So this is a research question. For this one, we needed to characterize the shredded tires. We need to make sure that shredded tires have high hydraulic conductivity so that water can drain through it very fast. No clogging, and it should have adequate shear strength and interface strength so that the material is stable on slopes, and it should be durable. And also, in terms of the performance of any shredded scrap material, any waste material that you look at in applications, it has to be equal or better than conventional materials that you use, right? So in this case, granular soils or geocomposite that we use as a drainage material, otherwise, so the use of shredded tires should be comparable to the performance of using granular soils or geocomposite. So to answer this research question, we had to do several research tasks. So first thing what we had to do was to look at, tire shred size and engineering properties. And then we had to look at clogging potential of tire shreds. And we had to look at the transmissibility of tire shreds. We had to do some hydrological modeling. And we had to look at the interface shear strength and stability of the slopes. And then once we did all those things, we designed a field system and we constructed it and monitored the performance. So these are the things that we had to do for this project to demonstrate that shredded scrap tires indeed can be used as a drainage material, and they are demonstrated to function well in the field scenario. So I'm going to go through each task very briefly. So tire shred size and engineering properties. So this is very important consideration if you are going to do research in this on this topic. So scrap tires, you will have all kinds of sizes, depending upon what the source is. So we are not generally using scrap tires, as they are. I know in some places they may be using it, but it's very hard to use those as scrap tires as a whole in many applications. So one thing I mentioned is crumb rubber or rubber fine. You can use this in asphalt, or you can use other small applications. And the other one is called tire chips. If you can reduce them to smaller sizes, talking here between 12 and 50 millimeter size, and you take out most of the wire out of that. So this is tire chips. By the way, tires have like a steel in it, so that's could be an issue. And the other one is called rough shred. Basically, this is the larger size shreds. And so what is the difference between these three things? So when you shred them in a shredder, in a commercial shredder, as a first pass, you get this one, rough shred. So when you put a whole tire into a shredder, and then other side, you get this rough shred. So in one pass, you get this one. But if I want to get this tire chips, I need to process it. You need to go through it again. You collect all the shredded material first time, you put it again and shred it and shred it and shred it. And you may have to take out the wires if steel wires if it's needed. Or if you want to make the crumb rubber, you have to process it further. So from economically talking, from economic point of view, the rough shred is going to be very cheap to produce. For tire chips, you have to spend money, and for crumb rubber, you have to spend a lot of money. So which one you want to use? So in our applications, in many civil engineering applications, you prefer to use this rough shred. So you want to use the tires and go through once through the tire shred, and whatever comes out outside, so that generally is more than 4 inches. So that's we call it a rough shred. So if you can use the rough shred in your applications, you're going to save a lot of money. Otherwise, shredding cost is going to be high. So in our research, we said, if you can shred it into small size, you can use that one as tire-derived fuel. I mean, of course, you have other problems. But if you want to use a tire-derived fuel, you have to reduce to small size. But if you have to use in civil engineering applications, if we don't have to do that one, if we can use the rough shred, we're going to save a lot of money in shredding operations. And if we are going to use the rough shred, how do you determine the properties? We need to know the properties of, the tire shreds, whatever size, whatever way you processed, because we need these properties in our design calculations. So we did a comprehensive literature search, and this is the paper that Arvind published. We looked at the literature, we looked at, okay, what size tire shreds people have tested, what are the properties. So we looked at the unit weight and hydraulic conductivity, compressibility, and shear strength. We were looking at, tire shred versus the properties. And I summarized all the properties in this table. They range quite a bit, right? Because, the tire size, the tire chips, a lot of people, do the lab test on very small tire size chips, So, but if you're trying to look at the size of rough shred, you don't find a lot of, testing done on those kind of large size tire shreds. And also people use different type of testing equipment and procedures. So we found out that it's very hard to, collectively look at all the published data and make any sense out of that. But here I've shown you the minimum, maximum, mean, standard deviation based on, mixing apples and oranges and everything that is from the literature. So it's less useful, but when you're talking about rough shreds, you need to plan on testing yourself. But the bottom line is, irrespective of which study that you're looking at it, what size you're looking at it, you come to the realization that shredded tires are lightweight materials, highly permeable materials, high shear strength materials. They are durable materials. But the only problem with these materials is the high compressibility. You need to keep that one in mind. Okay, so all the properties are great if you are trying to use as a drainage material, but the compressibility is the one that you need to take into account in your design. So what we did is, okay, what we wanted to use, rough tire shreds, and then we got some samples of those, and then we did some testing in the lab. So this is me some years ago. How do you do the grain size distribution of tire chips, especially if you have big tire chips? You cannot put them in the sieves and then shake them like what we do for soils. And so what we had to do is basically take some large amount of representative tire chips in big pan like that, and basically you take one chip at a time, you measure the dimensions, and you measure the mass. I know it's tedious, but if any of you can come up with some better technique, let me know. but that's what we did it. And then you can plot tire chip size versus cumulative distribution, either based on the weight or based on the quantity. So you can do both of those, but it gives you a good idea about size distribution. You can get an average size. The purpose is fulfilled. Okay, but it's a manual process that you have to do. And then we did compressibility testing. Basically, you put them in a big container and start loading. But in our case, remember, we are trying to use these shredded tires as the drainage material in the landfill final cover. Maximum that you could have weight on the top of it is like a 1 foot or 2 feet of soil layer, cover soil layer, and maybe some construction equipment loading. So we're not talking about large vertical stresses. So when you compress, when you apply the load on shredded tires, you will see that lot of compression. So it's close to 30%, under 30 kPa load. And you unload them. Of course, you're not going to come back to zero. So this is the permanent deformation that you have. And then you can load it again and unload it, load it again and unload it. You can see this, compressibility behavior. As I mentioned, the tires are more compressible, so you have to be, taking that into account in your design. Permeability. So you cannot use those standard permeability equipment that you have in your lab, right? So you have to create this large-scale permeameter. And then, you follow the same procedure. Just the size of the permeameter has to be big. And, you can do the same constant head test. So we have the tire chips in this cylindrical setup. We have, this is the 30 centimeter inside diameter and 83 centimeters or like 100 centimeters total is the cylindrical permeameter that we built. And then you put the tire chips in there, and then you have perforated plate on the top and put the water. There's a constant water source there, and then constant head. And then you measure the outflow and calculate the permeability, just like a constant head permeameter test. But here, we have a loading frame where we can load it. The idea was we apply some load and note down how much is the compression, and then measure the permeability. And then we keep doing that one under different normal stresses. So we had to develop our own large-scale permeameter. One thing that you have to keep in mind is that what you have to measure what is the outflow capacity before you put anything, right? So that is going to limit the permeability calculations. You can have only so much of outflow. If your material has the, could have outflow more than your equipment, so that's the limiting factor. So you cannot measure the permeability more than outflow capacity of your permeameter. So you need to, check that one first and then look at it. So this is how, our permeameter look like. So basically, it's a simple PVC cylinder, and we have outlets, the water inflow and other things. And I still remember the day that we were doing these experiments, because when you have very light load on the top, and then when you put water gushes through the outlet. The tire chips are so permeable. We had to use these buckets. I had like 2 students, 3 students. They were sweating, just changing these, buckets, and then we had to weigh them on a big scale and other things. So it was, huge amount of flow coming. And then when we started, applying the stress, then the tires get compressed, the flow becomes less and less. And when we applied certain level of stress, you see that the water outflow reduces so much that we had to use the graduated cylinder to measure the outflow. I hope you can see the graduated cylinder. So you can see the effect of compression of these shredded tires on the permeability. And this is very important to consider, especially if you are using this as a drainage material. So here are the results from this test. As I said, when we didn't have any any pressure on the tire chips, the hydraulic conductivity, we could not measure it because it's more than the outflow capacity of your permeameter. So we cannot, that's like, I don't know, 3, 4, 5 centimeter per second, 10 centimeter per second. We don't know that one because we could not measure, with the permeameter with the outflow capacity that we have. But as soon as we applied some pressure, I'm looking at here, high pressure, and you can see the compression is about here 50% compression under this. I forgot how much is the load, 150, 170 kPa. So there's a 50% compressibility. And then you could measure the permeability of it, which is 1 centimeter per second. So still really very high. I know in cover system, we're not going to go, much higher than these stresses. So we know that, permeability is going to be high, but we tested this one because during that time, we wanted to see if these tire chips can be used as a drainage material in the bottom liner. And, if you use as in the bottom liner, you have a lot of waste, right? At the landfill that we're looking at it, there was like a 200 feet, 300 feet of waste that's going to go on the top of it. So we wanted to simulate that stress conditions. And if you look at increasing stress conditions, you can see the permeable, compression increases initially fast, after that, not that much. Eventually it was like 65% compression, but the permeability, you see this one, it reduces orders of magnitude. But still under even 1000 kPa pressure, we had a permeability of 0.01. Generally 10 to the power minus 2 is the requirement for the permeability of drainage material, either in the drainage in the landfill base liner system or final cover system. So we still meet that requirement. But I must tell you that when we were measuring these permeabilities, when you apply these high stresses, and we were waiting to stabilize the outflow, but that creep effect comes in. So the creep effects keep on reducing the outflow. So we waited as long as we could, but in a real situation, you could anticipate that you could have still creep, compression, and that might further reduce it. Who knows, what would be the ultimate hydraulic conductivity. So I have reservations of using shredded tires as a drainage material in the bottom liner system, but I have no hesitation of using these in the final cover system because you're not going to have that much stress at all on the top. So after looking at those properties, I will appreciate if you can mute. Somebody's background is coming. So I appreciate if somebody can mute, please. So please everyone mute. Okay. So then looking at the clogging potential, we looked at this. This testing is specific to application as a drainage material in landfill cover systems. So remember in cover, so you have a shredded tires and you have a soil cover on the top of it. This is like a vegetative cover, or erosion protection layer. So you have the top. When it rains, you're going to have water passing through the soil and then passing through the drainage, the shredded tire drainage layer, and that will take care of the lateral flow, right? But as the water is passing through this soil layer, what is the potential for that soil to infiltrate into this shredded tire layer and clogging up the tires and reducing the permeability? Okay, so that was the concern that we have. As the precipitation infiltrates to the cover soil layer, the soil particles might get into the tire shred layer, and that may clog the shredded drainage layer. So do we need a geotextile between the soil and the shred tires? So basically we simulated, we got the soil from the landfill where we're going to use this as the thing. And then we evaluated two types of tire shreds here. Then, we did some tests without geotextile and we did some tests with the geotextile. So we did a bunch of experiments, varying the tire shreds, our soil layer thickness, geotextile, and normal stress. So this is our testing program. I'm going to, upload one paper that we wrote, so you can get more details on this one. So we did a bunch of these experiments. As I said, we changed the tire size, cover soil thickness, geotextile used or not used, and we simulated some normal stress. And so the whole idea was, this is the testing. So same permeameter that we use for hydraulic conductivity, we use that one here. So we simulated, that drainage layer here, and then we put a soil layer on the top of it, and we are simulating the infiltration, and we are looking at the outflow. And then after testing certain period of time, we take out the soil, we take out and we measure the hydraulic conductivity of the tire chips. So we know how much amount of soil actually infiltrated into the shredder tires, and what is the effect of that infiltrated soil on the permeability. So we were able to do this one. Generally, I don't wear the suit and tie when I go to the lab, but for some reason, I don't recall what was going on that day. So, and so this is the picture I was able to find in my old files. So these are the results. Shredded size, shredded scrap tire size. How much is it? Our soil thickness. So without going into a lot of details, the results are as expected. If you don't have geotextile, so the soil is going to infiltrate. And remember, the tire chips have almost 60% porosity. So the pores are partly going to be clogged up, but still, you have enough outflow. But obviously, if you can provide a geotextile, so there will be a little bit of reduction in the flow rate, because maybe the soil is clogging up initially the geotextile a little bit, but after that, you will see maintaining the high flow rate. So the results are not very surprising, but what is surprising is that you don't have the entire soil layer eroding and clogging up the hydraulic conductivity. So we did the test with different soil cover thicknesses and different shred size, and then we found out that the conclusion out of this one is that if you can use a geotextile, you are going to solve a lot of problems. So these are the results. If you don't put the geotextile, there's a lot of amount of soil from the cover soil is going to get into the shred tires. So you're compromising the integrity of the cover soil. Even though nothing is happening, not much is happening to the shred tires, because it's a high porosity, you still have porosity for the flow. As you see here, on the right side is the initial permeability versus final permeability. Final permeability divided by initial permeability. So there's like a 25% reduction in the permeability if you don't use the shred tires. But still, the permeability is way high. But you can see amount of cover soil that infiltrated. If you don't have geotextile, then you have more of that. So which you don't want to see that. So the conclusion out of this one was, hey, it's important to put a geotextile between the soil cover and shred tires. So one may think, hey, you don't have to do this test, because you have contrasting materials, so you throw a geotextile anyway. But remember, we're trying to save as much money as possible. If it is not needed, we don't want to use it. So, but we find that the geotextile is needed. Now the other question is about transmissivity. What is transmissivity? Is basically, think about this one. You have a barrier layer at the bottom, you have shredded tires layer here, and you have a cover soil. So we looked at the clogging with the infiltrating water from the cover soil going into the shredded tires. But now what we're looking at is, when the water goes into the shredded tires, you're going to have a lateral flow, because you have a slope, and then water is going to go through this drainage material, and it's going to get out of the landfill. So while the water is flowing laterally through the shredded tire layer, what is the potential for this cover soil erosion? What is the potential for this barrier soil erosion? And what is the clogging potential of these shredded tires as a result of that lateral flow? So we are concerned about that one. So again, the question here is, do we need to put a geotextile at the bottom between the barrier layer and shelter tiles layer? And do we also need this geotextile? We said that we need it for clogging potential. Will that help also in the transmissivity issue? So we created this transmissibility testing apparatus. Basically, we created this profile. We let the water go from this end, and then water, basically, this is the clay, this is the clay, so water tends to go towards the shelter, through the shelter tile layer. It goes through it, and then water comes out, its outflow, and comes out here. And then, after the end of the testing, we can calculate the transmissivity. And then we can find out at the end of the testing how much is the cover soil eroded, how much is the barrier soil eroded, and then we can analyze those things. Again, we did a nice testing program to evaluate this. Again, we changed the tire size, geotextile used at the top, geotextile used at the bottom interface, in the combinations that you see, So we don't put it in the top and bottom. We put only, bottom, and we don't put it at the top, all these nice combinations that you can do it in the lab, right? So that's the advantage of doing control tests in the lab. And then we also looked at with no normal stress and with the normal stress, basically, simulating the cover soil layer on the top of it. So, these are all the variables that you could think of, and you did all the tests. Again, not going into a lot of these details, providing that geotextile at the top interface is crucial. And it didn't make much difference whether you use the geotextile at the bottom interface or not. So with that conclusion, you can see that there was not much of erosion from the barrier soil layer for all the conditions that we looked at it. But if you look at, if you don't put a geotextile layer on the top, even during the lateral flow, you could have a lot of soil erosion from the topsoil. But if you provide the geotextile, between the top and the shred tires, cover soil and the shred tires, that will lead to very low change in the infiltration, and then it won't basically affect it that much. So if you can provide geotextile on top and bottom, that's okay. But it's absolutely essential to put a geotextile at the top interface, and you don't have to worry about putting a geotextile at the bottom. So after studying these things, we did some hydrological modeling. Basically, we used the HELP model. Anybody who works in landfills, they are familiar with this. I teach this analysis in my landfill design class. So we simulated different profiles. So here is the cover soil without putting a drainage layer. So this is the 24-inch barrier soil layer, and you can have a 24-inch vegetative cover layer. And there's no drainage layer whatsoever. Here is the drainage layer is provided between these. So this 24-inch, 24-inch, this is 24-inch, 24-inch, and in between is a 12-inch of drainage layer. Here I use the conventional sand material as the drainage material. And here I am using the shredded tires as the drainage material, and 12 inches. So I have hydraulic conductivity properties, the thicknesses, and then when I input into the HELP analysis, you can do the parametric analysis and evaluate all these design variables that you have. And then what the most important parameter that you want to look at is what is the hydraulic head on the top of the barrier layer. So here is you have a barrier layer, you have a cover layer, here is the drainage layer. How much is the head that you're going to accumulate, maximum hydraulic head on the top of the barrier layer? So that you can analyze based on this. And for the three, without going into a lot of other details, just showing the main result, if you don't have any drainage layer, you're going to have a lot of hydraulic head on the top of it. So that shows that this could really impact the slope stability, and you're not draining out. So all the infiltrated water is going into the waste, and waste as is becoming leachate. So obviously you don't want to have this as an option, but just for analysis, you can see what happens if you don't have a drainage layer. But if I use the sand as the drainage layer, it works good. Like, you have a 5 inches of leachate head. So the regulations don't allow more than 12 inches. So that's the kind of a regulatory requirements. If so this meets the requirement. But if you use the tire sheds, because of that high permeability, much more permeability than the sand layer. So basically you have the same thicknesses, but tire sheds have a very high hydraulic conductivity. So as a result of that, the hydraulic head is going to be much lower. So which is good. So we're basically showing that. And you can see that makes the difference in terms of slope stability. Could somebody mute their mics, please? So then the question is about slope stability and interface strength. So we know the shear strength is very high, but what about interface strength? So we did, these interface tests. Basically, putting the tire chips on one side and the other material on the other side. Maybe if it is a geotextile, we just, anchor that. And then we shear it. And you have to be careful because you have, the size is a constraint, of course, in all these things, the rough shreds, even if you make it much larger, you will everything equipment size up, scale up, but still, questions arise, are you measuring right way or not? But, you have to do your best, in these kind of situations. So this direction, then we tested the interfaces that we could potentially have in our proposed cover system. So remember, you have a barrier layer, and we don't have a geotextile there. We're not going to put a geotextile, and we're going to put shredded tires. So you have a shredded tire and a soil as your one layer. And then on the top of the shredded tires, we're going to have a geotextile. So you have a shredded tires and geotextile interface. And then on the top, you have a geotextile and the cover soil. So basically you have these interfaces. So you have a geotextile and tire sheds right at the top interface. And then tire sheds and the soil interface, like at the bottom. And then you have soil and the geotextile interface on the top. So you could see these interfaces. These are the only interfaces that you will see in our proposed cover system. So when you do these interface tests, you get really high values of interface friction angle. And you expect it because, shredded tires, right? You cannot really, shear anything to it. They offer so much of resistance. So this is good. So what does that mean in terms of slope stability? So you don't have to do the fancy, slope stability analysis. The infinite slope stability analysis is commonly used for analyzing the cover system. So if you look at that one, so these are the equations that you can find. You can find these things from any textbook. So the factor of safety is given here, and you apply this one instead of friction angle. You put interface friction angle, and calculate the factor of safety. And factor of safety is a function of this hydraulic head in the drainage layer. So what I'm showing here is just doing some parametric analysis and plotting these results. If you don't have, it's completely dry, let's say, there's no accumulation of water in this cover, 0. So then if I have a 2-to-1 slope, my factor of safety is 2.5. If I have 2.5 to 1 slope, my factor of safety is 3.25 or something. And if I have 3-to-1, it's close to 3.75, close to 4. So what you need is 1.5. This is 1.5 in here. So we have absolutely no problem in meeting the minimum factor of safeties. You can go up to 2-to-1. But, remember we talked about what is the potential for clogging, accumulation of this leachate head. So if you look at a worst case scenario, so if there's, let's say it clogs up completely, and then, head is HW over H, that height of water this occupies the entire layer, this is for 1, let's say. Generally, we have these slopes, cover slopes 3:1. If I have 3:1 slope, even if it clogs up completely, your factor of safety is more than 1.5. So we are fine. If it is 2.5 to 1 slope, you see this, the factor of safety is, not 1.5, but it's like less than that, but it's higher than 1.2. So if you assume that, this, head built up is temporary, your factor of safety of 1.2 is fine. So it still meets 2.5 to 1 slope. But if you have 2:1 slope and if it gets clogged up, then you have to worry about it. Okay. So the drainage, you have to ensure that drainage occurs properly and there's no leachate head. But based on this analysis, 3:1, that's common slope, no problem. But you can also go to 2.5 to 1 slope because you have these abandoned landfills where you don't have luxury to grade them flat. Okay, so you can go steeper, 2.5 to 1. You can go with those kind of slopes. Still, you will not have any problems whatsoever. So we resolved all those issues, through our lab testing and analysis. Now we are confident that our system can work. So, but you have to show it works. You cannot just say that it will work based on our lab research. You need to go to the field. So we actually, did this demonstration at one landfill called the Collinville landfill. And before we did anything, the site looked really bad. You see the erosion, and you see the leachate puddles. It's a mess. And that's why, this landfill needed fixing, right? And first thing what you do is the grading, right? So as a designer, if you're going to go put the goal here is to put a nice cover and put a gas collection system. That's all. And so grading is very important. You have to grade it overall so that you have that good surface water control, right? So the water runoff control and all the drainage that comes out from the drainage layer can be controlled. So that's the one which you need to make sure through the grading. Then what we chose is that we didn't do for the entire landfill capping because this is research and they wanted to see whether this will perform or not. So we selected an area here about 1 hectare and 0.8 hectares was for shredded tires, and then this one was a sand. So basically we wanted to construct 2 cap systems, one with the shredded tires and other one with the standard sand, so that we can compare, side by side, whether, using the shredded tires is comparable to the standard way of doing it with sand. So we had these 2 sections. One section is the tire shreds, they're using as the tire shreds as the drainage layer. Other one is using sand as the drainage layer. So the cross section will look like this. You have seen this before in hydrological analysis, 24 inches of compacted soil barrier layer, and you have a drainage layer, and you have vegetative covers here. So it's shredded tires, and we recommended using the non-woven geotextile on the top, so that geotextile is there. So this is basically our design, right? And then standard design is the same, except this material is a sand. And we know exactly the permeabilities of these materials. We assumed this, based on our testing, actually the permeability could be more than 1 centimeter per second. When we said, okay, let's use 1 centimeter per second, and the sand that was used at the site, we got the sample and we did the testing on that. So here are the sand and the shredded tires. And shredded tires, as I said, is, we didn't want to use the small size because that does not make any sense from economic point of view. So we wanted to use large size, that rough shred I was talking about. So the rough shreds that we got was from a close by facility. There was a jail. The prisoners volunteered to work, and there was a company that was doing the shredding operations there. So we got the tires transported from there to the site. So not too much transport distance. So then first thing what you do at the site is, clear up that existing surface, and then grade it. where you need some soil, you put it, and wherever you have enough soil that is existing already, um, just adjust the moisture and compact it. Basically, this is what you show here is, clearing everything and grading it and making sure that this barrier soil layer is properly compacted. So your barrier layer is in good shape. Then after that, we put a shredded tires. So this is the 12 inches of shredded tires. You just go there and place that one. Uh, and this was done only that experimental area. And then you have this non-woven geotextile on the top of it. And then this is the cover soil that goes on the top of it. So remember, 24 inch, 12 inch, and 24 inch geotextile and 24 inch is cover soil. So that's it. And this is another sketch of the same thing. So you have a barrier layer, a shredded tires layer, and geotextile, and on the top, and that, the cover soil that you put it in. And one thing that comes to mind is that, okay, do you need to use any special equipment and special personnel for the construction? Absolutely not. So same equipment that was used, for standard construction was used to handle these shredded tires, placement, everything was done with using conventional construction equipment with, regular construction personnel. So you don't need any special expertise or equipment or personnel to do that one. So then what we did is, we had a barrier layer and we put a shredded layer, we put a geotextile, and then we realized once you put the cover soil on the top of it, the infiltration through the cover soil would take a long time and we will not see any drainage. By the way, two things that we did. One is we put some pipes through this drainage layer. This is along the slope and you can see the outlets. I will show you in another picture. So that's one thing. The other thing I want to mention is between this shredded tire layer and the sand layer, we put a clay berm so that these two sections are separated out. And just to check the drainage performance, we got, the water tank and then water truck, and then we just sprayed the water on this some designated area, and we collected the outflow at the other end. So here is the inflow. Basically we're trying to simulate how much is kind of infiltration directly on the tire shed layer, and we were able to measure how much is that infiltration rate is. And then there's a pipe that goes underneath and comes out at the other end. These are my students helping out, and we were measuring how much is the water that's coming out, and then we are weighing how much is the outflow is. So based on this simple analysis, I mean we did this one on the shredded tire layer and also on the sand layer. So they give a simple comparison. It's the infiltration rate is high compared to the sand, and outflow rate is high compared to sand. No brainer. That's what you expect, but we need to generate the data to demonstrate that this in fact happens. So you have good drainage performance through the shredded tire layer. So then we wanted to, put some flow meters at the outlets so that we can track outflow that's coming out. And we wanted to collect the samples, outflow samples, because, there's another question that always comes to mind is, hey, are you going to leach out some contaminants out of these shredded tires? Are you going to contaminate the surroundings? So we wanted to, analyze the outflow quantity, but also we wanted to see outflow quality. And then we wanted to look at erosion and vegetation growth, settlement and slope stability, any kind of fire hazard. So we wanted to look at that. And this shows, this is the outlet pipe. This is Arvind, young looking that time. It's exit pipes. And then we had some these flow meters because this site is very far away from Chicago. So we wanted to make sure that this outflow is recorded, just like the water meter. So that one, and then this is how we were able to we put the bucket at I don't know if you can see here, but like we attached the bucket at the end of it, and whenever we go there, we have a sample collected, there was not much of flow through that. I mean, it didn't rain that time, but whatever water that got collected in the at the outlet at the buckets, we were able to um, collect it. But in terms of the outflow volume, it was not significant. We had like flow meters that can measure high volumes. We expected a lot of volume, but there was not that much volume coming out. So then we analyze the outflow samples. This is the chemical contamination issues, if you want to think about it. So we collected the sample in November 2001. I'm telling you, this project is done a long time ago. This is the sand section, and this is the tire section. So look at the numbers, okay? So many of them are below detection limits. You had a calcium, and then this is the tires is 4.4. It's even lower. And iron was there in the sand, but not much here. And so you can see, there were no big issues. So all the toxic metals are much lower. I mean, very, this sand is something, but metal, this shredded tires didn't have. So you cannot make, conclusions out of small differences, but there's nothing coming out. Then you look at, after almost 2 years, right? October 2003. Which is rare to go back after two years and look at the outflow sample, and we did that one, and you see no toxic chemicals out of this one. This is very important because you could do something leachability test in the lab, but this is in the field, right? And also after 2 years, and only thing that comes out from this testing is this iron. I mean, you look at it, they are very close to sand. Only difference that you see huge difference between the sand sample and tire sample is the iron. So the sand has 2.2 and tires at 400. So this could be, due to the steel that was present in the tires, and some of it could be that some of that could be contributing that one. So other than this elevated iron, there was no other issues with this one. So we go to the site, we look at it. This is me, posing with my, test pad here. So my test pad is right here, goes around here and comes down here. My outlets are around here. So I go there and look at it, just the visual observations. There's nothing else, of course, other than collecting the outflow samples. We look at the vegetation, erosion, any subsidence, settlements, and then slope issues. So no problem. And again, we need some witnesses to, agree with our observation. So there are people from IEPA and other people coming and seeing that one. So we go to that site at different times. So beautiful. I mean, you cannot really find out unless I tell you where the shredded tires are. You cannot really distinguish the difference between shredded tire section and other sanded sections. So grass was growing fine, no issues, no erosion problems, no slope problems, no settlement problems, right? No fire problems, nothing. So good. Sometimes, having problems, makes the projects more interesting. Hey, we had this problem. So, but in this case, everything was so good that, everything works perfectly. It's amazing, right? And this does not happen all the time. So sometimes when things happen so good, you don't have much to write about. So you don't get a lot of papers out of these kind of projects when you have all the successes, right? You can just write in one sentence, there were no problems. So that cannot be a paper. So in closing, we identified local environmental problems. I want you to, take these as lessons in terms of what you could do it, okay? So we identified the local environmental problems. You could do the same thing. So the problem that we identified was scrap tires and abandoned landfills. So we proposed a practical, effective, and economic solution, right? So think about what you could do to your local problems, okay? We don't want to come up with some fancy, solution that is not practical and is not economical, right? So here we are trying to solve two problems with one solution, and we assess the solution our concept through lab testing and modeling. I always believe this, that, before you go into the field, play around in the lab, try to understand, effects of different system variables, understand the fundamentals, you know, because you could afford to have failures in the lab, not in the field. So if you find something didn't work, that's good, great lesson to learn in the lab, and that, you don't repeat it in the field. So it's important to address technical issues, through controlled lab testing, and modeling is extremely important to scale up and look at different variables, because even in lab testing, you can do only a certain number of tests, not a lot of them. So um, you can validate your model through that limited testing, and then use the model as a predictive tool to look at other conditions. We did that, and then we gained the confidence. Once you do that one, I always believe that if you design a solution based on the fundamentals, it has to work. So, I mean, you feel confident that it's going to work. There could be other situations that you didn't consider in the lab that may lead, not working, but you feel confident that you did your best. So we performed the field demonstration, and we collected the field performance monitoring data, and this we used large quantities of scrap tires, and we used the rough shreds, as I mentioned, and use of standard construction equipment and procedures were shown to work, and we documented and disseminated the study results for broad adoption. And it's being used at other sites. You don't need research again and again on this. So this is proven at one location. If you have same kind of situations, you can do other locations. Only thing is you don't get too many publications out of this. So given the solution, people can take it and run with it. It doesn't have any patent issues or anything like that. So I don't believe in patents, unless you come up with something that can make you rich. And this is another site where these tires were used for the same purpose, and successfully. And when you do the research on the problems that impact the society, you get a lot of publicity. So these are, I'm going to show you some newspaper articles that time. Shows you, here's it. Professor seeks to dispose scrap tire problem. Here is the engineer finds solution for environmental headache tires. New life for old tires. I mean, it's a lot of fun. I mean, news reporters calling you and wanting to know what you're doing. If you do, hi-fi research, you don't get calls like this. But if you work on the problems that affect the people, affect the environment, and normal person can understand the impact of your research, you get a lot of publicity. So, the Earth Day was yesterday, and so, this UIC professor helps the Earth. UIC professor develops cleaner way to scrap tires. And just, I talked to this reporter over the phone. He was able to understand and sketch this figure, sketch this sketch. I mean, I didn't even, contribute anything, but they were able to understand, these things easily. So here are the publications that you could get that provide you all the information that I presented in this for more details. One other thing that I want to mention, if you work in this shredded scrap tires applications in civil engineering, you must look at this ASTM standard 6270. Standardized terminology, standardized specifications for tire-derived aggregate, and they also give you some example, properties. So always having standards makes a lot of difference. So if you have a standard, then everybody believes that everybody can follow it. So ultimately, the research can lead to some guidance documents. Not everything translates into ASTM standards. So that's my presentation. And here is the contact information. And if you have any questions, you can contact me. And I'm going to stop here, sharing the presentation here, and take any questions that you have. So I'm not tracking time, anything, because this time I'm giving the presentation. I'm also monitor. I'm also moderator. So I could go as long as I wanted, I guess. But I hope I made justice to your time. Hopefully you learned something out of this, and you will make me happy if you can do some research based on what I presented. So it's not very difficult, but you can do it. Okay, so with that one, I shall stop sharing. I want to look at these questions. So let me see.